Okay, so here we're going to take a look at a Simpson's rule. So this one's a bit different, though previous to the midpoint and the trapezoidal, kind of based on geometric formulas of finding areas uh, of geometric shapes being rectangles or trapezoids. Now we're going to take a different approach here, right? So given a curve here, right, and again we have our usual breakdown of subintervals where x of 0, that's our initial point, and then x of b, that'll be our x sub n, right? And we still do subintervals of length delta x, right? That still remains the same here, right? They're equal subintervals here. The partitions are equal, but instead of some geometric shape, what we're going to do here is across two consecutive subintervals, we're going to create, right? So we'll call those point P0, point P1, point P2. And then again, the point here is x naught f of x1, x1 f of x1, and then x2 f of x2. All right. So across these 3 points here, we're going to create a parabola. All right, and then here across these next x2, x3, x4, etc., right, across those 3 points, then we'll have another parabola that we create. All right, so and I won't go through the exact proof here, right? There's a breakdown of it in our textbook here, but the idea here is that, well, it's a parabola, so essentially it's an integral that can be done using simply the power rule, right? So our polynomial here is a of x2 plus bx plus c, right? And we can solve for those coefficients a, b, and c with the fact that the function and the polynomial share these points, right? P0, P1, P2. They are on the polynomial we use to approximate the function, but they're also on the function itself, which means that P of x0 is equal to a x0 plus b x0 plus c, but that's also our f of x0, right? Or our y sub 0, right? The y value. 0, and then P of x1 is ax1 plus bx1 plus c, and then P of x2 is equal to a of x2 plus squared, excuse me, these are squared, plus b of x2 plus c. Right, and that's our f of x1, f of x2. All right, so kind of manipulating this algebraically and then solving for a, b, and c in terms of x1 and x2 and x naught, right, we're able to evaluate this integral here, the integral from x naught to x2 of f of x, right? Hold on, getting a little sloppy here. So the integral of x naught to x2 of f of x, right? That's approximately the integral of x naught to x2 of my polynomial p of x dx. Okay, and then we do that for all of the consecutive parabolas that we have across the subintervals from a to b. All right, and as it turns out, doing some manipulation and then some combining of the like terms, right, the one requirement here is that for Simpson's rule, n does have to be even, right? N is even, right? Delta x is, as always, right, they're regular partitions, so they're all equal, so it's just b minus a over n. N is even, and as it turns out, after kind of deriving this formula, the Simpson's rule, which we'll use capital S sub n, is equivalent to delta x over 3 f of x naught plus 4 f of x1 plus 2 f of x2 plus 4 f of x3, etc. So it has this behavior of the coefficients where it starts at 1 and then it alternates between 2 and 4. So 2, 4, 2. All right, and then lastly ending on 4. So 2, 4 of f of x of n minus 1. And then the last one is always just, the coefficient is always 1. So it starts with 1, it ends with 1, and then alternates between 4, 2, 4, etc. All right, but again, we must have n subintervals, right? Even number of subintervals. So again, the setup here, let's set up one same example we've been working with before, where we had we want to evaluate the integral from 1 to 2 of 1 over x dx, where now I'm going to have n to be 10. All right, so my delta x would be 2 minus 1 over 10, which is 1/10 or 0.1. Okay, so our x naught starts with 1, right? The beginning of the interval. X1 is 1.1, etc. till we get to x10 to be, or let's say x9 would be 1.9, and x10 would be 1.8. Okay. So now approximating this integral using Simpson's rule. So s sub 10 would be 0.1 over 3, right? Delta x over 3. And then the setup would be, again, we start with f of 1. Then we start with our coefficient 4, f of 1.1, plus 2, f of 1.2, plus 4, f of 1.3, etc. We keep going till we get to plus 2, f of 1.8, plus 4, f of 1.9, and then lastly f of 2. Okay. All right. And again, right, I don't expect that we're doing this by hand, right? It's just a lot of repetitive calculations. So we set up here our numerical integration, right? So we have our function. We just have to adjust what we have here. 1 over x, and we want to increase n goes to 10. Okay, and I also want to turn off the trapezoidal rule, and then the Simpson's 1/3 rule, right? All right, so there we go. So that is our Simpson's rule here that we see here, right? And the parabola are just the segments here in between those intervals. Okay, and then just to get an approximation here for the Simpson's rule, here we get 0.69315. All right. All right, and just kind of looking across the different values. So we've done the midpoint, which is 0.6928, and then the trapezoidal rule, which is 0.6937. All right, and then the Simpson's rule falls kind of in between those. All right, and it is an approximation that really, if we do the analysis, it's a combination of the midpoint and the trapezoid, that it will always fall in between those values there.